Hello. So I'm gonna start off. I right at the top, so I imported all of these things that I knew I was gonna need to use. Some that I didn't necessarily use, but didn't hurt. So first off, I started off by loading the data that we were given, and then I did have to specify that we were separating it by the semicolons and not just the commas. That way they would separate it out, and that worked just fine. Then the first question talks about if there's any class attribute in our data set. I think that the class attribute, based on reading that little table of the description of the column descriptions that professor provided, I determined that G3 would be the class attribute because that was the final grade. And a lot of times grades is one of the most important things that we look at when it comes to school and other things. And then what political purpose would someone be interested in this? Well, people in the education system or politicians passing policies on education could look at all the different things that impact students' final grades and try to make changes to those things in order to help students learn more and obviously get better grades in school. Because if they could do something to improve that, why wouldn't they? So then for the list of minimum, max, mean, median, mode, and then Q1, Q3, and standard deviation for travel time, study time for students younger than 17 and older than 18. So this is it right here for students younger than 17, and obviously here is me selecting the specific columns. So column 2 is age, column 12 is travel time, and then column 13 is study time. So we see the mean for travel time is 1.55, and then for study time is 1.9. And then for students older than 17, we see that the mean is first travel time 1.61 and study time is 1.97, so it is a little bit higher. But then we do see that the standard deviation for the different columns is higher for it's higher for students who are younger than 17, so that just goes to show that students who are younger than 17, they kind of have a wider variety of people who are traveling. So there's students students younger than 17. There's some that travel a lot, versus there's some that travel a little. And then same thing for study time. There's some that travel a lot, well, there's some that travel. Study times. There's some that study a lot, and there's some that don't study that much. And then we do see that travel time has a smaller standard deviation than study time, so travel time is a little bit more consistent than study time. So there's more variation between how long students study for. And I just wrote that all down here. And then creating scatter plots. So this is the scatter plot for travel time and final grades. And we do see that as travel time increases, so going down the x-axis, that grades overall decrease. You see that with this high travel time, there's not a whole lot of grades up here like there is when travel time is a lot lower. Then this is the scatter plot for study time and final grades. So we see that typically students who spend more time studying have high final grades, although this is not a very strong relationship. I'm just gonna go ahead and just add that here because as you can see, it's not a strong relationship. Because obviously there's students over here who don't study that much, but they still manage to get some higher grades, and vice versa, students who study a lot but still get pretty low grades. And then over here is age, scatter plot of age and final grades, and we do see that typically younger students seem to get higher grades than older students. We see these older students, so past the age of 18. We see over here, they have much lower grades versus although those who are 18 and younger have more consistent grades, a little bit higher. But there are some outliers, but overall they do have higher grades if they are younger. So for the K-nearest neighbors, I just started off by importing all the things I was going to need in order to actually do the K-nearest neighbors, and then I decided to find the optimal K just to get the best results. And then I'm looking at K's between 1 and 5, and then increasing it by 2's. And then this is just me running it and seeing how accurate that would be. Anywho, so then I ran it to find the optimal number of neighbors, and I see right here it is kind of a little bit harder to tell, but it is between 30 and 40, so it tells us right here that 35. It's almost the same here for 40 something, but why are we gonna run more nearest neighbors if 35 would be just fine? Then over here I make the smaller data set that just has age, travel, study time, and final grades because that's what we were asked to look at. And then I make everything else be the X, and obviously G3 be the Y because that's the final grades and that's what we're trying to predict. I then do the test set and the training set, and right here, this function actually automatically is by default 75% training and 25% test splits, which is what we were asked to do. Over here, I'm just specifying that I do want to have 35 nearest neighbors since that's what our optimal K was predicted to be. Then over here is just the predicted values. In order to evaluate really what that means, we get the test score, and the test score is 18, so not all that high, but that's, I guess, the best we could do since we did use the optimal K. And then as you can see, predicting that the predicted values versus the original values, and we're just comparing those. So in some instances it was correct, as you can see right here and right here, but then there's also a lot of incorrects, which could be expected with a test score of only 0.18. Then over here I did the confusion matrix, and as you can see there's a lot going on since there are several different final grades. But I guess it was best to predict these types of grades. So I guess the average grades, which is expected because we would predict that students would more or less score averagely. A lot of time we did see that it predicted that students were going to get an 11, but really they got a 10. And this is the position score. Like I said, we're not really surprised that the model did best at predicting like average scores, since most students probably did get average scores. So that explains that. Over here for the neural network, I just went ahead and set up the data set once again with the attributes that we're taking into consideration. Named it student and end for neural network. Over here, I just went ahead and scaled all of our variables that we were taking a look at. As you can see, these are the scaled values. And I did that using the standard scalar package. And then I was splitting the data, and over here I did have to specify that 25% of it was split. So that's meeting the criteria of the 75% to 25%. Then I built and trained the model. So this is me building the model using the MLP classifier. And you can see all the iterations and how the loss as we go down is increasing, as it started over here above 1. It started very high. I think it was actually above 2. But then, what was it? Yeah, above 2, but then it ended up being only 0.88, I guess we could say. And then if we print the score, we actually get a pretty high score of 0.7. So the neural network was a lot better at predicting final grades than the k-nearest neighbor was. And this also shows with our confusion matrix, we see that a lot of the high numbers are correctly predicted values are diagonal. So that goes to show that these values were predicted correctly. So that's good. And then same thing with the precision score. And then I also said that a classification report does not make much sense here, since it is expected that the final grades are in the middle, since that's where students score overall, like I mentioned earlier, the average score. So here I'm doing the hierarchical clustering. So I use G3, which is final grades, as an index instead, like we were asked to do. And that's just showing what that looks like now. And then over here, I'm once again using the standard scalar to scale all of that and normalize it, if you will, all of that data. You could see that's what it becomes here, just putting it back into the data frame, because over here it's like an array. We want it to be a data frame. And then right ahead over here, we're doing the iterations. figure out what clusters we are getting and what predictions we're making. And then over here we're finally plotting what our clusters or hierarchical is predicting. It's hard to read, but you can see it's broken down into two big groups, and then from there they're broken down into a bunch of smaller ones. Then the second one that I ran was k-means. So first I defined this elbow plot because I know that if we were using k-means, we were asked to use the elbow plot. And then so that's just defining it, and we did say that we want to take from the student 3 norms. So the normalized data, we're taking into consideration age, travel time, and study time. And then I found it to be about 4, the elbow to be right here. So I went ahead right here and specified that I wanted 4 clusters, and then just ran it to have the labels made and what those labels looked like. And then over here, we're actually creating the clusters. And I did say that if you scroll all the way down, that they were not particularly, the clusters don't particularly make sense to me because I was expecting for them, I know we're making 4 clusters, but more or less I expected it to be something like, one cluster with high final grades, one cluster with low final grades, like maybe like 2 in the middle or something of the sort. But if we scroll through the clusters, we see that that's not necessarily the case. We have clusters in this one alone as low as 7 and as high as 17. So that's kind of like low, average to high final grades. And then that is also the case for the other clusters as well. So this second cluster, we see that there are very high grades like 16, but then also very low grades like 8. And this is something that continues throughout all of the clusters, so I didn't think they particularly make much sense. So finally, what kind of political decisions could the Secretary of U.S. Department of Education make on the basis of the classification and cluster analysis that I did? And I would say that they should build schools in places where students won't have to travel a long distance to go to those schools, because we did see an association between increased travel time and decrease in final grades for students. So when politicians are deciding where to build schools, that's something that they should take into consideration. And then I would also encourage them to tell kids to study more, because we do see that there is somewhat of an association between study time and final grades. It's nothing major, but there is somewhat of an association. And then overall, we did see, since as students got older, it was likely that their final grades decreased. So maybe people in the U.S. Department of Education could make programs specifically for students over the age of 17 to do well in school, and that way that kind of helps close the gaps between older students and younger students.